So this would be the second half of the notes for Unit 1 Kinematics, Part A. And we're going to specifically talk about some of the vectors and what does that mean. First off, we should have an understanding of what do these colors of the vectors mean. We try to make sure that we all are using the same color as much as possible. So when you're looking at somebody's drawing, you're able to determine what they're kind of showing you. Okay? Now, I understand it's not always feasible to have 5 or 6 different colors of maybe pens or colored pencils. But one of the things I think we can use is our technology allows us to use different colors. We can use Notability or other writing apps and change the color so that they follow suit. Some of the examples that I do today will not have these colors specific. However, when we get into moving forward with them, the colors will be very specific. And when we draw out our examples, I will try to make sure that the colors follow this as well. Okay? And it is suggested, as always, to make sure that we do this. We use this for vector quantities. Displacement, velocity, acceleration, and forces are known as vector quantities because they have both direction and magnitude. Just like Vector in Despicable Me. He commits crime with both direction and magnitude. Which can be very helpful when trying to remember what is what. So we use silly things like that. Many of you probably didn't catch that the first time you saw Despicable Me. Science teachers did. Add some humor. So where does this play into account? To add vectors graphically, for us at least this unit, we are going to make sure that they're always moving in one direction. Not the band, just one direction. We add them together, and that is called the resultant. The resultant is the sum of the two vectors. The resultant is the sum of the two vectors. Now, in the example from the picture that we can see, your house 5 meters. Now, is that a realistic distance? No, it's not. 5 meters is, that's a little short of this room. So it's obviously not realistic value there. Could it be 5 kilometers? Probably more realistic. That's about 3 miles. Then maybe another 2 kilometers. Another 1.5 miles or so. 1.25 miles. Okay? So the example here, we just use meters. But it could be kilometers and it wouldn't matter. Maybe it would make it more realistic. But if you go 5 kilometers to the store and then go another 2 kilometers to your aunt's house or friend's house, whatever, what was your total displacement? 5 plus 2. So it should be 7. We could say the same thing. How far, if you go to Jordan, how far is that? Well, it's about 7 miles, right? Now, what if you stopped off at the yellow barn and then went all the way? Okay? You would just add your stops in. Ultimately, the distance that you traveled, or the displacement that you traveled, is still going to be about 7 miles. A little bit of on and off, small minor details. Now, what we have to be careful with is with vectors, we need to have that directional component added to it. And in displacement, because it's a directional component, if I make a round trip, how far from the center did I, or from the beginning did I say now you go from your aunt's house back to your house? Your displacement from where you started is going to be what? 0. The displacement from where you started is 0. That's where distance and displacement are going to vary. Your total distance would be the 7 that you went to your aunt's house, and then the 7 back, which would give you the 14 total, but the displacement ends up being 0. And it gets into some, some philosophical things where if you run around a track and run the 400 meters, did you do anything? Well, technically, no, you didn't go anywhere. But you ask anyone who's run the 400, and they would say, no, I did something. But then the same thing would be if you go downstairs in the weight room. You deadlift. Lift the bar up, and then you set it down. Well, the equation for work is force times distance, or displacement, actually. If you're lifting it up and then putting it back down, the displacement is 0, and we all know that anything times 0 is going to be 0. So even if you deadlifted 500 pounds, you didn't do any work. But anyone that would lift would tell you, no, that was a lot of work. Well, technically, by definition in physics, not any work. And so therefore, we have to understand the difference between real-world talk as opposed to physics and science talk. And sometimes they don't match up. They contradict each other. So we have to be careful. And this is why drawing out is so important. One, a lot of us are very visual learners. We want to vision it, but sometimes how you convey that vision from what's in your head to what's on, to say your work shown, is very important. It's extremely important to me as a teacher to know where you're thinking or how you're approaching the problem. This is why when we say show your work, I can look at it and say, okay, I see where they're going here, or I can look at it and say, they have no idea what they're doing. They're just writing down a whole bunch of stuff. in hoping something sticks. Okay, so it's important to do that. Now we say and talk about this coordinate system, and a lot of you may have heard that term before, coordinate system. Basically, you're looking at X and Y systems. Is something moving in one direction as opposed to moving in another direction? Sometimes we can just use, instead of X's and Y's, north, south, east, west. Never eat soggy watermelon. Never eat soggy Wheaties. Never eat sour watermelon. Never eat soggy waffles. However else you want to, there's a lot of different ones out there. So an object moves to the east. That would give us that arrow. Something moves south would give us that arrow. At some point, we're going to add the two together, but not yet. Okay? So therefore, it's again good to draw out so we can see where everything's going. Now the coordinate system north, east, south, west also can be utilized in an X and Y coordinate system. When I was in high school, the best thing that ever helped me, and I've seen students struggle with which one's the x-axis, which one's the y-axis. The y makes a y. Y-axis makes a y. And so that helped me out, and because then the other one is just kind of a 50-50 shot, right? You know one, you got the other. Kind of a deal. So whatever it is. And again, it's good practice. I don't know why I've had many students over the years, I go, draw it out. Draw it out. And they're like, but I'm like, no, draw it out. It's okay. And if it's wrong, it's wrong. That at least will help me determine where you're coming from. Or why you have certain things if it's confused. When they're added together, it's very easy. When they're subtracted from each other, it's always from where you start to where you're currently at. So in the first graph here, we can see my start point is at 0. Goes 8 kilometers, stops, then travels 6 more kilometers. So 6 plus 8, 14. In the second example, travels 8 kilometers, maybe goes, oh crap, I'm going to run out of gas. Maybe I need to go back. It only makes it 6. How many kilometers from the gas station are they? Or how far do you got to walk? And that becomes the, where's the gas station at? And how far from where you are? You are 2 kilometers east of the gas station, or the 0 point, or the point in which you start. Now, do we have to write out east every time? No. Could easily just write out 2 kilometers with a capital E. But the arrows help us visualize what's happening. So, car travels 4 kilometers north, stops, and then travels 3 more kilometers north. Are those arrows pointing in the same direction? Yes. Because they're pointing in the same direction, we can just basically add them together. Oh, I think I can do that. Bottom there. Those two together should equal out a bigger arrow, which should, 4 plus 3 is 7. But is that the story? Is that it? No. It's not just 7, it's 7 kilometers. Because there's a difference between 7 kilometers and 7 meters. One's over 4 miles, the other one's way short. You'd want to make sure that the person, say if you're going bungee jumping, knew the difference between kilometers and meters. If they cut off 7 kilometers worth of bungee cord and you only want 7, you're going to go either splat or have a good ride. Okay? You don't want to go splat. Okay? Not only that, it's 7 kilometers with what? The direction. And then in this case, north. Again, you can write out north if you wanted to. You can write it out as 7 kilometers north, or just the 7 kilometers with the capital N. Either or would work just fine. What happens when they're not going in the same direction? This time we can use some terminology or bring in some terminology that we haven't used yet, and that is the change or delta the triangle is used or is sometimes seen as the Greek letter delta. A lot of times in science, we say it's the change. The change in displacement. So if a car travels 5 kilometers west, then travels 2 kilometers east, what is the resulting vector? Another way of saying that is What is the change in position? Okay. Doesn't matter which way we use it, it's either a resulting vector or what is the change in position. Starts there. Then turns and travels. If here was the start, the black dot is the start, blue dot is the end. We want to, connect the dots, right? Well, it would be best if they were on the same line, but so we have the purple arrow in this case so that we can kind of see the difference. How far from the start? Where is the change in the position? Even though they stopped, went one direction and then the other, we still have that. And 5 minus 2, like I said, we have to know some basic math. 5 minus 2. 3. Labels. Paying attention to that. Kilometers. Now becomes the, well, what direction? And that's where drawing out helps us out. Because the purple arrow isn't pointing in what direction? It's pointing in the west direction. That's how we know what the answer is. Question. Would my answer be different if I added my vectors differently? Would my answer be different if I said we're going to start going east? So my start point is still going to be the black dot. And then I travel west. Has my answer changed at all? From my start to my finish. Oh, my answer hasn't changed. It's still 3 kilometers west. Which brings us to another point that ultimately, if you add your vectors correctly, It actually doesn't matter the order in which you do them. They should equal the same. They should both equal 3 kilometers west. Now, if you're looking at this on a number line, it would be a negative 3 kilometers. But we're using a coordinate system of the northwest, east, south. And so therefore, we can just say west and not have a negative number. And we can have negative displacements in physics. So you can get negative numbers in physics. You just have to be careful about it.